Well, welcome to the heat pump water heating technology deep dive. We'll be discussing some really interesting concepts today. Presenters today from Association for Energy Affordability. AEA is dedicated to achieving clean, efficient, and equitable zero net carbon multifamily building stock in California. I'm Ari Usher. I am a project manager at AEA and joined today by my colleague Ashley Davis, a senior engineering associate at AEA. And also we've got Aaron Keller, senior project manager on the California Electric Homes program, who's hosting this webinar. We will hear a little bit about the Electric Homes program and the great offerings there, and then jump into our content on heat pump water heating. So we'll first start with some fundamentals, and then a bit of a deep dive into unitary heat pump water heating and central heat pump water heating, design considerations, and a lot of hows and whys. So then we've got a quick section on maintenance and operations, and then overview of the no-cost technical assistance available through CalEHP. And then we'll have time for discussion at the end. So you should see a poll right now. We want to see who's joining us today. So if you could just take a moment to enter your role. Would love to hear who we've got on the call. Always interesting to know. Great. So I'm not sure I'm seeing answers coming in, but looks like we've got our answers there. So thank you all. Oh, awesome. Okay, looks like we've got some across the board. Builders, equipment manufacturers, property owners, and a couple others. So awesome. Thanks for being here. All right, so we'll get started with California Electric Homes overview. I'll pass it over to Erin.
Thanks, Ari. And thank you all for joining us today and choosing to spend some time with us. I'm going to introduce the California Electric Homes Program, also known as CalEHP, as you'll hear me calling it. This program provides technical assistance and financial incentives to builders and developers who are constructing new market rate and all electric properties. And really, this program is intended to help support new construction best practices, drive energy savings for homeowners and tenants, and support California's energy policy goals. So a little bit about the program. We are all electric new construction program, and I'll talk a little bit more about what all electric means to us and the incentives on the upcoming slides. But a couple things I want to highlight here. Our territory does cover all of California. We are a statewide program. We're not specific to different IOU or electric gas utilities. We are the whole state. We do also support a variety of building types, including single family, low rise and high rise multifamily. And we also support accessory dwelling units, modular construction, as well as manufactured homes. So no matter what you're looking to build, we can likely support it or would like to talk to you about how we can support it. And when it comes to income restrictions, this program is specific to market rate. If you are an affordable housing builder or developer, the California Energy Commission does administer another program called Build that is meant to complement this program for our low-income housing. And then for incentives, we'll talk more about these on the upcoming slides, but we do have a variety of incentive offerings through this program. We have a base incentive for all electric new construction. We have incentives for energy storage. We also have a variety of bonuses if you're looking to install especially efficient equipment or improve the envelope of your building, or if you're located in different areas such as a disadvantaged community. We have bonuses for all of those scenarios. And as we'll talk about more today, we do offer no-cost technical assistance to support you in your build. So I've said all electric a couple times. We're going to define what that means specific to the program on this slide. In general, we mean that there's no gas hookups to the property and that the following equipment eligibility requirements are being met. So for heat pump, space heating, and water heating, those do need to be heat pump technologies rather than electric resistance or gas. And then on the cooking side, we are talking about induction cooking to be eligible for the program. And then on the bottom row, we have thermostatic mixing valves, segregated circuits, and communicating thermostats. These are meant to support the performance of the equipment or the homeowner or tenant's interaction with the equipment. So we'll talk a little bit more about thermostatic mixing valves today. And we do encourage folks, if you are interested in participating, to be talking about these requirements with your project team early and often to make sure that you're eligible for the program and are able to stay enrolled. And our team's also available to support any questions you have, and we have resources on our website as well specific to these requirements. And if you do choose to install those equipment options to qualify for the program, these are the incentives that we're looking at. A couple things that I want to point out here. The first being that these incentives are not de-escalating, meaning they are the same whether you are completing your project in 2026 all the way through 2028. So as an example, for a single family home, it'd be $2,500 per home for meeting those eligibility criteria we covered on the last slide. If you're located in a disadvantaged community or hard to reach area, you'll see that those incentives are higher. As an example, $3,000 for that single family home. One other opportunity I do want to highlight that is unique to this program is battery storage incentives. So if you're looking to add an additional resiliency measure or improve the value of your build, we do offer financial support for battery storage. That incentive is $250 per kWh or kilowatt hour. Or if you're located in an all-electric REACH code jurisdiction, that incentive increases to $300 per kWh. If you're not sure if you qualify for that higher value or you have questions about how to include battery storage in your project, we're more than happy to walk through that and discuss those options with you. That is what I had to cover as far as introducing the program. I'm going to hand it back to Ari now to talk us through more about heat pump water heating fundamentals.
Thank you so much, Erin. Those are some great incentives that we've got here in CalEHP. So I hope that piqued some of your interest. But regardless, heat pump water heating is something you may want to know more about. So we're going to go into some fundamentals here. Really quick, we do have another poll question here. Wanted just to know, are there any preconceptions that you have about heat pump water heating? Um, what are your thoughts on it? Maybe some of you have done a lot of heat pump water heating. Maybe you've worked in all electric reach code jurisdictions. Um, Maybe you haven't done it before or haven't done it a lot. So great. Awesome. Looks like a lot of folks, think that it's more efficient than traditional systems. That's definitely the case. Um, Thank you so much for those answers. All right. So let's get started here. What is a heat pump? Well, we all live with heat pumps around us. Most simply, it's a device that moves heat from one place to another using a refrigerant. So refrigerators are heat pumps. Air conditioners are heat pumps. With heat pump water heating, what we're doing is taking heat from the surrounding air and transferring it to water to heat that water up. What's so great about heat pumps? Well, they are hyper efficient. So they're 3 to 5 times as efficient as gas or electric resistance equipment. And this is really because the electricity is not being used to heat the water directly. It's just being used to run the compressor that is moving heat from place to place. So we can get very high efficiencies here. Heat pumps enable zero emissions buildings via carbon-free electricity. They improve air quality, so no local emissions by taking combustion appliances out of the dwelling units, out of the buildings, no local emissions. Also got improved safety here, no gas lines to the buildings. Um, and specifically for space conditioning, heat pumps can actually deliver heating and cooling within a single system. So some space efficiencies there. And heat pumps work in many different climate zones. Heat pump technology has come a long way, especially in California. There's no climate where a heat pump is not going to work for domestic water heating. So how do heat pumps work? Just really quickly, the refrigeration cycle um, on the low pressure side, heat is absorbed into the refrigerant. And then on the high pressure side, that heat is released from the refrigerant. So this can be reversed for heating or cooling. For the water heating application, we've got heat being absorbed from the ambient air and being released into the water. Some of the components of a heat pump water heating system, whether this is unitary or central, we have the heat pump itself. So you can see there two heat exchangers, the air to refrigerant heat exchanger, and then the refrigerant to water heat exchanger. And in that side, um, cold makeup water comes into the heat exchanger, gets heated up, and is delivered to the hot water storage tank. So heat pumps are always paired with typically a large hot water storage tank. Storing water at a high temperature, upwards of 140 usually is definitely suggested. A mixing valve should always be included in a heat pump water heating system. That mixing valve then is going to mix that hot water down to the delivery temperature, usually around 120, and deliver hot water to the end use. Some different configurations and options. Unitary heat pump water heaters. This is a one-to-one equipment to dwelling unit. Here we've got both integrated or packaged tank options and a separate tank or split options. So in the integrated tank, it looks, similar to a storage gas water heater, but there's actually a heat pump in there. And then for that separate tank option, we've got a smaller capacity heat pump compressor paired with a storage tank. And there's actually only one manufacturer I know of that's offering a split system at the scale, for a single dwelling unit, and that's Eco2 that creates the Sandin system, which is pictured there. And then for central application, there are a whole bunch of equipment options, typically larger capacity heat pumps paired with storage tanks. That's what you're going to see a lot of. There are also larger capacity integrated tank options for central application as well. So a couple of important definitions when we're talking about heat pump water heating. First is recovery rate. So recovery rate is the amount of hot water a system can produce in 1 hour, and that's assuming a 90-degree increase in water temperature. So how much hot water can the system produce in 1 hour? When we're comparing heat pump water heaters to traditional combustion water heaters, the recovery rate is longer. So that is definitely something to design around. It's just a condition of the equipment itself and the technology itself. Longer recovery rates. The other definition is first hour rating. First hour rating is the amount of hot water a system can deliver in 1 hour of continuous usage. And it's a function of the storage capacity and the recovery rate. So starting with a fully heated tank, how much hot water can be delivered in the first hour? So with heat pump water heating systems, the first hour rating may actually approach a comparable gas system. But again, this is starting with a fully heated tank. However, when we go into that slower recovery rate, it's not going to be able to deliver the same volume hour after hour. So that's definitely something to consider and design around. just a quick sizing example for the same building with gas tankless, gas tank type, or electric heat pump. You're seeing that um, to provide the full demanded hot water, the storage is actually going to need to be bigger for heat pumps. This is really to accommodate that longer recovery time. Storage is going to need to be sized to provide the full hot water needed to cover our peaks. And that's a little bit different than traditional gas systems. In terms of refrigerants, I mentioned these heat pump water heaters use refrigerants to move heat around. There are a couple of common refrigerants for heat pump water heaters, and they have different characteristics and play into then equipment options and choices, different pros and cons. But the ones that you're going to see most regularly are 134A. That's going to be in most integrated heat pump water heaters, that unitary kind of scale, and some split systems as well. Um, R744 is actually carbon dioxide. This is going to be in split systems and single pass systems. This has an excellent efficiency, does really, really well, and also performs really well even in low ambient temperature environments. And then we've got R513A, typically in split systems. This is a lower global warming potential refrigerant, compliant with, any upcoming refrigerant phase outs. And we'll go more into the equipment options and which refrigerants they use in a bit. Yeah, so just kind of in summary, with heat pump water heaters, we do face new challenges as this technology becomes more and more common. These will just be incorporated into our design. But for the time being, ambient air temperature is the heat source. So we always need to consider the ambient air temperature for the install location. And then heat pumps, they actually exhaust cool air. So cool air exhaust needs to be managed to maintain the heat source. And that's through including ventilation in designs. And then storage tanks have to be sized to accommodate longer recovery time. And then there are space and electrical capacity considerations. And then we have the additional elements as well. So as I mentioned, the mixing valves, sometimes electric resistance fringe heating or backup, and sometimes swing tanks. So just a couple more slides from me, and then I'll hand it over to my colleague, Ashley. There are a lot of manufacturers out there offering unitary heat pump water heaters. As of today, these are the manufacturers that I've seen, and more products are coming on the market, every day. So 240-volt systems, this is probably most common. These are hardwired systems. They do include an electric resistance element in the equipment. But in this case, a thermostatic mixing valve needs to be installed separately. It's not going to be incorporated into the equipment from the manufacturer. 120-volt systems. Now, these are pretty interesting because it's essentially a plug-in heat pump water heater. Can be plugged into either a shared or dedicated circuit. There are, different options out there. And oftentimes they do have an integrated thermostatic mixing valve. So the hot water can be stored, upwards of 120, up to 130 or so. And the integrated thermostatic mixing valve is going to mix it down to delivery temperature. But the thing about these is not all models have electric resistance backup. In fact, many do not. So it really becomes important to manage ventilation and install location. Yeah. And then there actually are some combined space and water heating systems out there. And, I would say recently a bunch of manufacturers have actually introduced some of these products. These are maybe kind of interesting for the market rate application. They can actually provide hot water for domestic water heating and hydronic heating in a single system. And some systems can even provide hot and chilled water, so space heating, space cooling, and domestic water heating all in one system. Um, when selecting unitary systems, a great resource is going to be the Northwest Energy Efficiency Alliance qualified product list. So NEA has publishes an advanced water heating specification and qualified product list. And NEA Tier 3 or above rated water heaters going to be super high performance. So this is a great thing to reference. So let's get into how some of this plays into our design considerations. And I'll introduce my colleague Ashley for this section.
Thanks, Ari. Yeah, let's talk about design. Next slide. So the biggest thing, honestly, that you have to think about when thinking about unitary heat pump water heating design is circulation, right? As Ari said, a heat pump removes heat from the outside air, puts it into the water. That means you're left with a bunch of cold air. So your heat pump is, when it's running, continuously exhausting cold air and continuously needing more warm ambient air. And we found that if the temperature difference between the inside of the heat pump water heating enclosure and the outside of the enclosure is more than about 15 degrees Fahrenheit, there's probably not enough air circulation. You're probably getting a pretty big buildup of cold air inside your enclosure, and your heat pump's not going to run efficiently. It's going to start relying on those electric resistance backup elements if there's too much cold air, because it simply can't pull any more heat out of it. So this means ventilation is really critical. It removes cold air from the enclosure and introduces warm ambient air so that your heat pump can run effectively. This can be achieved with ducts, with louvers. There's a bunch of different ways to do it. Next slide. So when it comes to ventilating unitary heat pump water heating, a pretty common strategy is ducting. Most of the integrated tank type heat pump water heaters out there have a way to be ducted. Some manufacturers even provide kits so that you can very easily hook up ductwork to either the intake or the exhaust or both. Strongly recommended to duct when your heat pump water heater is in a space that's very small or insufficiently vented, because it's just more deliberate about really removing the cold air. A lot of times we will see a louvered door for intake and then ducted exhaust to the outside. So, if you're in an enclosed space that might get too cold, it's a good idea to duct your exhaust, because then you don't really have to worry about having other sufficient ventilation, right? You've already sent the cold air outside your closet. Also, you might want to duct if you're inside a conditioned space where you don't want to just be dumping cold air on folks, especially if that water heater is located right in the room. Can be a little bit of a shock to walk past and get a blast of cold exhaust air. It's true that ducting does add cost, and it adds penetrations to the envelope, right? So if you're in a conditioned space, ducting to the outside can increase air leakage. It's not always required, the actual cooling load it adds is relatively minor. It's more about the comfort of, just dumping it straight on people walking past. So there's some things to think about when you're thinking about the ventilation strategy that you're going to choose. Next slide. If you're going to duct, though, it's really important that your ducting is unrestricted, right? You can see a picture on the right here of a unit that has a ducted exhaust, but there's a pretty big kink in the duct, and it's doing a hard 90-degree turn right after it comes out of the water heater. So there's a shrinking room study, basically, where some researchers tested a bunch of different ventilation configurations to see which one led to the best performance. So they did a couple different configurations with ducted exhaust and then louvers for the intake. And they found that when they restricted the duct by about 50%, which was designed to simulate kind of a bent, restricted, crunched flex duct, that it led to a pretty significant drop in COP because there was a lot more electric resistance usage, because that internal fan could not overcome the pressure of a restricted duct. So if you're going to duct, make sure you do it correctly and that your ducts are as unrestricted as possible. Next slide. So yeah, whatever ventilation strategy you choose, it's important to make sure it's done right. So For example, on the left here is an example of not ducting at all, but you can see that that exhaust fan is almost completely covered by the adjacent HVAC duct. So if you're choosing not to use ductwork, you have to make sure there's unrestricted access to both the intake and the exhaust fans, or those grills, so that there's proper airflow through the unit. If you are going to duct, it's important to make sure that the ductwork is nice and straight, that it's as short of a run as possible with as few bends as possible, and usually with at least an 8-inch diameter. Like you can see, this second picture from the left is a pretty good example of a fairly straight intake duct without too many bends. Same with the picture on the far right, another example of a pretty straight intake duct, whereas that one in the middle is a little more restricted. It's going to impact the performance more. Next slide. Another design consideration is to think about sizing. I'm sure many of you are used to sizing like gas water heaters with this table. This is from the California Plumbing Code, and it basically provides the first hour rating that is required for your water heater, dependent on the number of bedrooms and bathrooms that the water heater is serving. However, like Ari mentioned, heat pump water heaters are much slower to recover than gas tank type water heaters. And so that means you probably want to go above and beyond what this table requires to ensure that you're going to have a good amount of continued hot water access, right? If you're only looking at the first hour rating, after you've depleted that water after the first hour, it's going to be much slower to recover. People might run out of hot water. So the best thing to do when sizing unitary heat pump water heaters is to look at the first hour rating that the table requires. And instead of finding a heat pump water heater that has that first hour rating, you should actually find a heat pump water heater that has that much useful storage. It's the best way to make sure that you're really going to meet the demand at the building. A good strategy is to make sure the first hour rating, storage volume, and then you still are meeting plumbing code if your first hour rating meets the heat pump water heater first hour rating spec. But again, if you have prolonged periods of use, you could run out of hot water. Next slide. And then another key design consideration is including like a thermostatic mixing valve. This helps increase the storage volume without increasing the footprint. It's good for constrained installs and helps minimize electric resistance usage. And there's potential for load shifting. So basically, the idea with a mixing valve is that you set your heat pump water heater a little higher than your desired delivery temperature. So then you have to pull less water out of your heat pump water heater every time someone draws water at the tap. It's important to not set your mixing or your set point temperature of your heat pump water heater too high. A lot of these tank type heat pump water heaters go up to about 140 degrees, but they do start to lose capacity. They start to lose efficiency at those really high temperatures. And then you can't load shift any further if you're already at the max temperature. So choosing a temperature that's higher than you want it to be delivered, but not so high that you're compromising efficiency is going to help you really maximize the storage there. Next slide. And then something else to think about, especially if you're installing these inside, is noise consideration. So with tank type heat pump water heaters, if they're inside, you want to make sure they're not too close to bedrooms, and you want to consider space usage, occupant sensitivities to noise. There are ways that you can vent or like air seal closets to also help mitigate noise further. If you're installing one of those split heat pump water heaters where the compressor is outside, that can help with noise, because then you've just completely removed the compressor from the interior at all. But you want to make sure they aren't too close to like bedroom windows or too close to adjacent properties, and make sure they're meeting the noise ordinances of your AHJ. So like Ari mentioned, NEA does tiers of heat pump water heaters, and they don't just rate efficiency, they also look at kind of all the other features of a water heater, including the noise. So when you're looking at those like NEA tier 3 and above, you're not just looking at the most efficient heat pump water heaters, you're also looking at the quieter heat pump water heaters. So pay attention to those ratings. They can help guide you to choose the quietest water heaters. Next slide. So yeah, then you have to think about where these are going to be located. Garages for buildings, common locations. This is a protected outdoor space that's usually pretty big and may have air circulation in this space to require minimal or not at all additional ventilation. So sound and serious ventilation interventions are usually not a huge issue. You might have to think about low ambient performance though, because this is an outdoor space. Outdoor closets are another common location. This again is an enclosed outdoor space where you probably don't have to worry too much about sound, but because the space is smaller, there's less opportunity for natural convection of the air, and so you will need to intervene with a ventilation strategy, whether that be louvers on the doors with the exhaust pointed at a louver, or ducting the unit for proper air circulation. And again, when you're outside, you got to think of that low ambient performance. Interior closets are a way to get around low ambient concerns, right? It's probably warm enough inside the dwelling unit for the heat pump to operate efficiently. However, again, small space, you need to think about air circulation. You also need to think about sound when you're inside. Next slide. And then electrical is something to think about as well, right? Different units have different electrical requirements. Smaller 120 volt heat pumps that don't have backup are going to require a lot less electrical than a bigger, 240 volt standard 30 amp circuit model. So think about, what the electrical capacity at the building is, but make sure you choose one that's still going to provide adequate hot water. Next slide. And I'll hand it back to Ari.
Thanks. Thanks so much, Ashley, for taking us through those unitary design considerations. Let's move on to central heat pump water heater systems now. So we've got here a piping schematic for a single pass with a swing tank type plant. This is currently the California Energy Commission prescriptive baseline for central heat pump water heating systems. Here at AEA, we like to do a little exercise called pretend you're a water molecule. So I'm just going to take us through how this works. The cold water makeup comes into the system and comes through the single pass heat pump water heater where it's heated up to upwards of 140 degrees typically. And then that hot water is delivered to the top of a large storage tank. With the single pass system, this is going to be a stratified storage tank. So if there's no draw on the system and the heat pump is running, that storage tank will get fully charged starting at the top down to the bottom over whatever the recovery time is based on the size of the system. So then you've got a fully charged tank. As soon as somebody is going to use hot water and turn on their tap, then that hot water is drawn from the top of the storage tank, which again is always going to be the hottest. It comes through the swing tank. Now, the swing tank is not actually designed to be a source of primary heating. The water is already going to be really hot coming out of the top of the storage tank. Swing tank does have a heat pump or electric resistance element in there, but it's not going to be actually doing the work of heating up water for delivery. So we're coming from the storage tank through the swing tank, still at 140 as an example, and then coming through the mixing valve here, where it's mixed with cold water and delivered to the building. So for multifamily, for these central systems, you're usually always going to also have a recirculation system. So that's where this recirc pump comes into play. When there's no demand on the system, the recirc pump is going to be circulating hot water through the pipes to keep them primed, and then returning hot water returned back to the system. So as that water is going through the building piping, it's going to lose maybe 5 to 10 degrees of heat. And we do want to make sure to maintain the stratified storage tank. So we're not going to deliver it back to primary storage. This is where the swing tank comes in. Hot water returned to the swing tank. And that element in the swing tank is really just for that recirculation heat loss load to bring it back up to where it needs to be to the set point. So that is our schematic there. Obviously, it's a little different. There are different configurations for multi-pass systems, but this is currently the prescriptive baseline. And talking about the Energy Commission, to be installed in California for a performance credit, a central water heating system needs to be certified to the California Energy Commission as JA14 compliant. This submission is completed by the manufacturer. And the current kind of state of certification includes a whole bunch of different manufacturers here, including, larger capacity and smaller capacity. I've got a table later that'll show kind of the differences between these different manufacturers and their offerings. Another thing to remember when you're selecting equipment is that a lot of different manufacturers are actually doing skid hot water plants. A skid plant is a plant that is built in a factory and shipped to the site, which really can reduce on-site complexity for the installing subcontractor. The heat pumps themselves, along with the storage tanks, all of the piping connections, the mixing valve, and often the recirculation pipe can all be packaged in a factory, and then on site, all that the installer has to do is attach the cold and hot water lines. So this can be really helpful, and oftentimes these skid manufacturers may actually warranty the equipment for longer than like a typical plumbing sub might do because they're doing this in the factory and commissioning everything. They're able to, provide potentially that extended warranty. Especially for maybe first time plumbers new to heat pump water heating or even designers or project teams newer to heat pump water heating. This may be a really good option. Also to reduce, overall construction time as well. So, and then of course there's other central heat pump water heating equipment that may not currently be certified. A couple of those would be, Transom, or IntelliHot. If you're happen to be working with a rep or a manufacturer that doesn't have their equipment currently certified, just encourage to go ahead and submit to the Energy Commission and get listed. Not that these can't be installed, but in order to be used for performance credit, they do need to be certified. So yeah, we talked a little bit about some of the different design considerations, but what are the criteria or what are the things about the equipment that play into this? So I want to just kind of mention the rated capacity. There's a variety of different sizes available. Usually for multifamily, we're not going to see the largest that's needed. That's maybe more for a commercial application, but maybe for a really large building. And then the efficiency, we've got some really great efficiencies, anywhere from 3 all the way up to almost 6 COP. The ambient operating temperature, some of these systems work really well, even down to, negative 25 degrees Fahrenheit. In California, you may not have a climate where you need to go that low. However, they also have the max water outlet temperature going up to 180. So a lot of different options there based on what you need for your project. Great. So some more design considerations with Ashley.
All right, let's get into it. Next slide. Yeah, so like I already mentioned, when you're sizing central heat pump water heaters, we're typically looking at more of an on large primary storage capacity, small primary heating capacity as compared to a gas system. To designing a central heat pump water heater that way, namely that it reduces overall hot water system cost, right? You could put in a system that's sized like a gas boiler and has huge primary heating, small storage tank, but it's going to be expensive. So we're going to require a lot of electrical capacity. Installing them this way also, reduces owner exposure to high peak demand charges. It reduces short cycling, and it can also help improve resiliency in the event of a power outage, because your really large storage tanks that are fully heated up can basically act as a thermal battery. This also enables load shifting and demand response because, again, you can rely on the storage, lock out the heat pumps during those peak pricing periods or demand response events. So yeah, looking at sizing the storage tanks to cover the peak load, and then the heat pumps to be able to recover that storage capacity during the off-peak times. There are some disadvantages to this, right? You might need really large tanks that are going to need more space and structural support than a typical design would. It can increase replacement costs. A 600-gallon tank is more expensive to replace than a 200-gallon tank, and it makes your plant more susceptible to distribution issues or really high recirculation loads. So designing that distribution system properly is going to be really important as well. Next slide. So again, just the example that Ari mentioned earlier, looking at a building just with loads calculated based on ASPE standards, you can see that the heat pump plant is going to have significantly more storage, but significantly less primary heating capacity compared to either gas configuration, which is going to mean that your recharge time is longer. Next slide. These are just some photos showing an example of this type of design in San Francisco, and you can see with that person for scale there, just how large these storage tanks can be sometimes. So you got to figure out where the outdoor units are going to be located and where the indoor storage tanks are going to be located. Something to think about with tanks of like that size is potentially can you get them through the door if one needs to be removed and replaced? So thinking about that, designing the space and designing the plant to allow for easy maintenance is a good idea. Next slide. So you also have to think about where the heat pump units themselves are going to be located. Most often we see these outside, right, on the roof, on the ground, in a garage. Occasionally we see them inside, but circulation was important for a small tank type heat pump water heater. It's going to be even more important for a commercial sized heat pump water heater. So if you are going to install them, make sure you're connecting with the manufacturer, following their guidance about having proper ventilation and air circulation. You may also need to think about the distance between your heat pumps and your tanks, right? It's a lot of piping. It's going to be running between them, and water cools down in the piping, right? It can dilute the tank if you have large volumes of water just kind of sitting in the pipes, cooling down when there's periods when the heat pumps aren't on. Sometimes you're even going to need an additional booster pump or tank between your heat pump units and your primary storage tanks if they're too far apart. You also got to think about sound, right? These can be much, much louder than those like residential sized units, pretty wide range of decibel ratings. So paying attention to the jurisdictional noise requirements and like adjacent buildings is important. And you may need to do interventions to dampen the vibration from the units, like isolators and rubber mounts and stuff like that. Next slide. And then you also got to think about ambient air capacity and like your rated capacity versus the unit performs at lower temperatures. So this is an example of Lochinvar's heat pump water heater, and you can see that the unit may have this maximum output capacity. Next slide. But that capacity and the COP start to drop pretty significantly as the ambient air temperature drops. So you got to look at your design temperature depending on where your property is located and make sure that you're still going to have enough heat pump to cover the load on those colder design days. Next slide. Here's just some more examples of what plants look like. This is an example of kind of an inside-outside install where your tanks are located inside and then the heat pump water heaters are located in the garage. Next slide. Another example of being fully outside on the roof with outdoor rated tanks. Next slide. And then you have to think about what type of heat pump water heater you're going to choose. They come in single pass or multi-pass configuration. Single pass configuration, exactly what it sounds like. It heats up the water from the incoming cold water temperature to the outlet set point temperature, usually about 140 degrees, in one single pass. These are the most efficient options and create better stratification in your storage tanks. They're a little more complicated. They also do not like to have warm incoming water like your recirculation water. So you probably are going to need some sort of separate recirc or swing type heater. But like I already said, single pass with a swing tank, pretty much standard practice. There are also multi-pass heat pump water heaters that operate much more like a boiler, where water moves through the unit multiple times in smaller temperature lifts. But these are a little less efficient. Your tank ends up less stratified, but they are simpler, much more like piping a boiler would be. Next slide. So again, you got to think about where your recirc water is going to go. You know, your warm incoming water. It's not what your single pass heat pump water heater. See some sort of swing heater installed as well, sending recirc water to the swing heater and to the mixing valve. Next slide. So again, like with the unitary situation, installing a master mixing valve at the building, really important with a central plant. Again, increases that effective storage volume, more load shifting potential, and it helps shift recirc water away from the swing tank back to the mixing valve instead, which can help minimize the electric resistance usage. So also pretty much always required, because heat pump water heaters, commercial sized, tend to produce water that's about 140 degrees, those single pass units. So pretty much required to make sure that you're not scalding people. Next slide. There's a lot of different types of mixing valves out there. Electronic and thermostatic are probably two of the most common ones to be used as a master mixing valve. Electronic mixing valves use temperature probes and then automatically adjust the ratio of hot and cold water to continuously achieve that mixed outlet temperature. They're pretty precise. You can and stuff, which might be important for commercial application, like where a building's not occupied at certain times or something like that. Thermostatic balancing valves don't need electrical connections. They're another form of automatic balancing valves. Basically uses a wax actuator to adjust the ratio of hot and cold water. They make these in both commercial and residential sizes. And then static mixing valves, typically wouldn't recommend these for a central plant because they don't adjust based on the hot and cold temperatures, right? You just kind of set them to a certain ratio and leave them alone, which means they can require a lot of trial and error and are much less precise. They can't really deliver like a continuous temperature. Next slide. And then choosing a recirculation control strategy is important as well, right? Especially if we have a plant where we have a swing tank or like an electric resistance water heater doing the temperature maintenance. We want to make sure we're not just dumping tons of water into that tank all the time, because it's going to run too much and we're going to drop the efficiency of our plant. So the objective here is to maintain our loop temperature with as little flow as possible. The best and easiest way to do this is with thermally balanced distribution system and a variable speed pump. This means installing thermostatic balancing valves on each of our risers or return loops, and then putting the pump in a pressure mode to react to those valves opening and closing. The nice thing about this is thermostatic balancing valves are pretty set and forget. You put them to a temperature and that's kind of it. You don't need to go through and, balance and calibrate the whole building. Just put them to a temperature and you're done. You just got to make sure your valves and your pumps are sized properly. Options like demand controls and aquastats are much less efficient and much more difficult to commission. Right? If you're using a different type of balancing valve, you might have to go through the whole building and like pressure balance them. And then demand controls and aquastats rely on temperatures of the return. And if you've got multiple loops, those pumps might turn off. even when a longer loop isn't fully heated. You should pretty much never be doing a constant speed pump that has no controls when doing a central heat pump water heating system. Next slide. And I think this is back to Ari.
Yes, it is. Thank you, Ashley. Um, yeah, pre-occupancy performance testing. So once construction is completed, but before the occupants move in, it's going to be a big benefit to the development to do some pre-occupancy performance testing, some lowercase c commissioning of heat pump water heating systems. And this is whether they're unitary or central systems. I think hopefully, you've seen that there's a bit of complexity in terms of the piping and the controls for central systems. With unitary systems, there are also manual settings, and when you both for the controls and for mixing valves as well. So for both system types, some pre-occupancy testing is really highly recommended. This is going to allow for the identification of issues before occupants move in. Nothing worse than getting occupants in and all of a sudden there's a whole bunch of hot water complaints. AEA, we've worked with projects to actually do some pre-occupancy performance testing, and with installers to develop, some kind of stress testing on these systems. Um, and we would be more than happy to work with, anyone that's got a project to develop some performance testing procedures if that's something you're interested in, adding in. So we could do that potentially through our no-cost technical assistance offering CalEHP has, and I will hand it to Erin to talk a little bit more about that.
Sorry, and if you wouldn't mind just moving us forward to the resources slide, I'll go ahead and just verbally cover the information. But as you've all heard today, Ari, Ashley, and their team at AEA have a wealth of knowledge when it comes to heat pump water heating and all electric equipment in general. And we're very lucky to have them as a technical assistance partner for the program. Technical assistance is a no-cost offering to you, even if you're not the primary applicant for the project. You can still apply for technical assistance as an architect, an engineer, an energy consultant, HERS rater. You're more than welcome to reach out to us to receive technical assistance, or if you have any questions, even if you don't have an all-electric design to begin with, if you're still using gas, we're more than happy to talk through options and review designs with you to make equipment selections. If you don't have a contact with our program already, you can use these methods here on the screen to reach out to us via phone, email, or our website. Or if you already are connected to our program, you can reach out to your assigned contact and inquire about technical assistance, and we're happy to get you started in that process. That is the content that we had prepared for you today. Thank you so much again for joining us, and I'm going to check in with Melinda to see if there's any questions for us, and feel free to throw any additional questions into the Q&A for these last few minutes.
All right. Some of them have been answered online, but this one has not. Have any analyses been done for large tank, small compressor scenarios on the benefits of added exterior insulation sleeves and such on the tanks?
Yeah, I don't know of any specific studies on that scenario. I mean, if you're installing everything outside, it's important to have tanks that are outdoor rated, which often have more exterior insulation. I don't know that adding extra insulation that's like not already there would do too much. There are standby losses in the tanks when there's not hot water use, but I don't know how significant tank insulation would be on that.
Okay, great. Thank you. We do have a very popular question that's asked frequently and often. Will these slides be available, and will a recording be available after today's presentation? And I can confirm that yes, indeed, we will post the presentation on the California Electric Homes website under our resources tab, and you'll get a short follow-up email following today's session with a link to that. So thank you to everyone who is able to join us, to those who ask questions, and if we can answer anything further, don't be shy, reach out. We'd love to support your project.